Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Irham Muhazzab bin Fauzi. My metric number is 083491.
My name is Nura Afifah binti Abdul Halim and my metric number is 081378.
Hi, I'm Nurul Ifah binti Rushdi. My metric number is 082691.
Hi, my name is Nurdana Hanya binti Ibrahim and my metric number is 082329.
My name is Faisha Najihah binti Saidi and my metric number is 083025.
My name is Marjana binti Mustafa Kamal and my metric number is 081922.
My name is Tana Batisha. My metric number is 082459.
Assalamualaikum and good morning everyone. We are from Group 4 and today we will present our analysis of a parallel algorithm, parallel merge sort, focusing on the critical path, word and span and Amdahl's law. For the introduction, merge sort is a classic divide and conquer algorithm. It works by dividing an array into smaller halves, sorting each half recursively and merging them to form a sorted result. Parallel merge sort improves this process by performing the splitting and merging steps simultaneously using multiple processes. This allows faster execution and better use of modern multi-core systems. Okay, so let's see task decomposition and distribution. Parallel processing begins with task decomposition, which is breaking a large task into smaller parts. And there are two common strategies. First, domain decomposition, where data is divided among processes, and second, functional decomposition, where different tasks are split. To be efficient, the algorithm must balance the load, reduce communication between processes, overlap computations with data transfers, and access memory efficiently. However, in real-world systems, more processes do not always mean faster performance. This is because the serial portion of an algorithm always limits maximum speedup. The critical path, like in merge sort, goes slowly but it still sets a floor for execution time. Synchronization is another challenge. For example, merging requires waiting for all sorted halves to complete before proceeding. This introduces delays in idle time. There are also overheads in parallel systems. Creating threads, scheduling tasks, and handling memory or locking mechanism all introduce costs. As more threads are added, these overheads can sometimes cancel out the expected performance gains.
Now, to evaluate performance, we use two key concepts, word and span. Word or T1 is the total number of operations of a single processor. For merge sort, this grows proportionally to n times the logarithm of n. Span or T infinity represents the length of the longest chain of dependent steps. This grows with the logarithm of n. Now, let's consider an array with 8 elements. To calculate the word, we multiply 8 by the base 2 logarithm of 8. Since that logarithm is 3, the result is 8 times 3, which equals 24 total operations. To calculate the span, splitting takes 3 steps and merging takes another 3, so the critical path has 6 steps in total. Amdahl's law helps us understand speed-up limits. Suppose 80% of a program is parallelizable and we use 4 processors. The speed-up is calculated as 1 divided by the sum of the 20% sequential part and by the parallel part divided by 4, which is also 20%. That equals 1 divided by 0.4, which gives a speed-up of 2.5. So even with 4 processors, the task is only 2.5 times faster. Now let's analyze using Graham branch theorem. We assume the total word is 1000 units. The critical path is 10 minutes and we have 100 processors. The execution time is calculated by dividing 1000 by 100, which gives 10, and then adding the span of 10, so the total time is 20 units. To get the speed up, divide 1000 by 20, which results in 50. This shows that even with 100 processors, the speed up is kept at 50 times.
Reflection on our discovery. Designing efficient parallel algorithms begin with understanding the critical path, word and span. By minimizing word and span, we can improve scalability and speed. But too much parallelism can lead to overhead from task coordination. A well-designed algorithm finds the right balance. Tasks should be small enough to speed things up, but not so small that communication delay slows every down. Achieving this balance is what makes parallel algorithms truly effective in practice.
This assignment has provided us with valuable insights into the core principles of parallel computing, using parallel merge sort as a practical case study. By analyzing the algorithm's work span and its performance using Amdahl's law, we gain a deeper understanding of how parallel algorithms behave and what truly impact their efficiency. This assignment also helped us realize that while theoretical models like word and span analysis and Amdahl's law are useful for estimating performance, real-world results also depend heavily on other factors. like touch granularity, communication delays, and system architecture. In conclusion, it highlights the need to balance theoretical potential with practical realities in designing parallel solutions that perform well in real-world computing environments.